Let's look at some sample homework problems from WebAssign. This is page 389, number 18, in section 5.2 in your book. You'll have about 5 of these in WebAssign. These will be short and easy. Express the limit as a definite integral on the given interval. So we're supposed to write the limit as n approaches infinity of the sum as I goes from 1 to n, x sub I star, square root of 1 plus x sub I star squared, delta x. We're given the interval 2 to 5. X goes from 2 to 5. And we're supposed to write all this as a definite integral. Well, remember, this limit of a sum gets translated into the definite integral symbol from 2 to 5. Then we just, in our notation, we drop the subscripts. We just say x square root of 1 plus x squared dx. By the definite integral from 2 to 5, x square root of 1 plus x squared dx, we mean the limit of this sum on that interval. And that should make us think of that 4-step process that we've been emphasizing. Partitioning 2 to 5 into n equal subintervals, picking a number, either left or right or endpoints, midpoints, whatever, in each subinterval, forming a rectangle over each subinterval, using f of x sub I star, that number we picked, x sub I star in each subinterval, using f of that number as the height of the rectangle, then adding the areas of the n rectangles and taking the limit of that sum as n goes to infinity. Okay, you'll also have a couple of problems where you're given a definite integral. So page 390, section 5.2, number 50. You're given a definite integral and you're asked to find the value of that by interpreting it as an area. Okay? Now we're going to learn a shortcut for evaluating definite integrals called the fundamental theorem of calculus in the next lesson. And we've learned actually to implement this 4-step process that's very lengthy and time consuming, and we only did it for a x squared function. So think about how complicated it would get if it was something else. But we've evaluated a definite integral using the definition of definite integral, that 4-step process. We're not asked here to do either one of those. We're asked to think about area. And the idea is to draw the graph of our given function. We know the area. It'll be a common shape, a circle, triangle, something like that, and use an area formula from geometry to find the appropriate area that this definite integral represents. So let's illustrate that with, again, page 390, number 50. Our given function f of x is 3 if x is less than 3. So if x is less than 3, the height of the graph is 3. I've graphed f of x equals 3 for x less than 3. And f of x is x for x is greater than or equal to 3. So when x is 3, right, when x is 3, f of x is x. So 3 3's on the graph. So this point gets filled in. Because when x is 3, 3's greater than or equal to 3. 3 fits in this bottom category here. The height of the graph is just x. So when x is 3, f of x is 3. Now when x is 4, f of x is 4. So I'm just graphing the line f of x equals x. That's this line that makes a 45-degree angle with the horizontal. Although mine doesn't quite look 45 degrees because my scale on the x and y axis is a little bit different. This line is just f of x equal x, but I only look at the part of the line where x is 3 or bigger. Now, I want to find the value of the definite integral from 0 to 5. So let me stop the graph when x is 5. 5 is a point on the graph. Okay. So the definite integral of this f of x function when x goes from 2 to 5 is just this area I have indicated I'm shading right now. That area, this area, A, is just the definite integral from 0 to 5 of f of x dx. So, do I know the area of this shape? Well, can't you divide the shape into a rectangle? It's really a square, but my scales are a little different, so it doesn't quite look like a square. A rectangle and a triangle. In fact, I could divide it into a rectangle, a square, and a triangle. Why don't we just do a rectangle and a triangle? How about this rectangle? You see the one I'm outlining? The rectangle with this corner, this corner, this corner, this corner. What's the area of that rectangle? Well, the width is 1, 2, 3, 4, 5. The height is 1, 2, 3. So the area is 15 square units. How about the area of the triangle that has this vertex, and this vertex? Area of a triangle is 1/2 base times height. The base goes here from 3 to 5. The base goes from 3 to 5, so that's 2. And the height goes from 3 to 5, so that height is 2. So the area is just 2 square units. So what's this total area A? Underneath this graph from 0 to 5, it's 15 plus 2, or 17. 17 square units is the value of this definite integral. We'll later learn how to do this algebraically.